All right, let's do this. So 3 things that you know about ionic bonding. Anyone willing to share something? All right, good. No sharing. That's hopefully one of the number 1 things you wrote. If they don't share, then what are they doing? All right, they're gaining and losing, or they're stealing. There's a complete transfer of an electron to another atom. Anything else that someone knew? All right, it's between a metal and non-metal. That will be true 99% of the time in this class. Go ahead, Peck. All right. And it's held together by ionic charge. Good. All right. The only, man, imagine if you had to read this right here. Really, the only one in this class that we will do that is an ionic bond that doesn't have a metal-non-metal pair will be if we start with the ion of NH4. NH4 is a +1. If it's with chlorine, it's a -1. This is an ionic bond because it's a bond between 2 ions. That's the only exception. Every other time, we will have bonds between metals and nonmetals. Well, I'm sure there's others, but I don't even know them. So pretty much that is it. Okay, we all right with that? Covalent we didn't talk much about. We will talk more. But what are 2 things that you might not know, or that you might know about this? All right, it can be the strongest. That's arguable, so it depends on the definition. They're strong bonds. Anything else? Okay, good. If you know 3 things here, you can get 2 things here because you just say the opposite. If ionic bonds don't share, then these must share. They share their electrons. Okay, that's 2 things. What's another thing we could get from here that we could put down here? All right, this is a non-metal to non-metal bond. Not really. I'm trying to think. The only thing I can think of that would be an exception, and you wouldn't even really have to do this, once in a while we have a polyatomic ion that has a metal in it, like permanganate, and then it bonds with a metal. That polyatomic ion is sort of covalently bonded to itself, but it's not to the other part. So that, like, even that's stretching it. Welcome. We've missed you. You feeling better? Lots? Good. All right. Getting pretty worried about you. All right. Is there, this was the last slide of the day, right? One thing you know about lattice energy. Hold on. Anything else?
It looks like lattice. Separate moles, solids.
Okay. Energy required to separate 1 mole of gas of that substance. Very good. That's the definition. All right. So we need to talk a lot more about lattice energy so that you can answer a few questions on your next exam, which is probably towards the end of next week. You all right with that? There's your warning. It won't be. All right. It might be in the middle of next week, too. I don't know. So let's talk about what lattice energy is one more time. If you remember, Young, with his geniusness, said a long time ago that you could find the ionization energy and the electron affinity and determine whether something was endo or exothermic. That was really close to being right, but we looked at the values and it turned out that that was not correct. So lattice energy was this third piece of the puzzle. And as Brennan had, it was the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. All right? Now, Jex, he asked me why this even matters. This matters because we always want to know about the energy required to break stuff and to make stuff. We will do some math with this eventually, but it's just important to know the energetics. We're going to have entire 2 more chapters in this book about the energy involved in chemical reactions. All right. The energy associated with the electrostatic interactions is governed by Coulombs-law, which is right here, but I'm going to put here on this different slide. This is Coulombs-law. I guess I should put, there is a constant, a K right here. It's not named after him, it's just a constant. It doesn't matter to you because anytime we use this, we're going to use it to compare 2 things, so the K is the same, so we can kind of ignore it. If you care, it's 9.1 times 10 to the 11th, if I remember right. That could be wrong, but it's close to that number if it's not right. It's a big number. I think I'm off 1 or 2. That's K. But once again, what's that? I will tell you in a second. I'm a little concerned that no one back there is paying attention. It's okay. You guys are still good, even if you spelled something wrong. All right. We ready to chop this up? Yes, sir. Okay, see you later. Good luck with that. Okay, I'm going to erase this because I don't really care about it. That's just a constant. Oh. All right. What this is saying is it's the electrostatic force. I just about spelled 4. That was funny. All right, it's the electrostatic force. It will be either attractive or repulsive. And it will depend on the charges that are involved, right? All right, so that's the electrostatic force of attraction or repulsion. R is the distance between nuclei, essentially, of the 2 things you're looking at.
So the force of attraction exponentially decreases as the further away.
Yeah. It's like why a magnet, it seems really strong, but even a very little movement away, all of a sudden it doesn't work at all, right? Because this is the law that governs a magnet. They don't work over very far distances. All right, then Q1 and Q2, they both stand for charge. So Q1 would be the charge of the first thing we're talking about. Q2 would be the charge of the second thing we're talking about. In this class, mostly, we will just care about the two charges. There is a little bit where we care about the distance between them, but it's pretty simple. So let's just use our brains. How can we make F equal a big number? All right, they need to be close. Oh, man. And? All right, big charges. And then obviously the opposite, for F to be small, they need to be far away. And small charges. You okay with that? All right, so what we're now talking about for the lattice energy in an ionic bond is it will be the charge of the first atom, which will be the metal, and the charge of the second atom, which will be the non-metal.
What would it be in case of NH4 and Cl?
The first would be NH4. The second would be the Cl minus. All right, and what we mean by charge is its ionic charge. So if it's in family 1, it's always going to form a plus 1 in an ion, right? Family 2 will always form a plus 2, 3, 4, plus or minus, so we kind of ignore them most of the time. But then family 8, it's going to form what? Not family 8. Family 5 will form negative 3, family 6, minus 2, family 7, minus 1. You all right with that idea? It's fairly simple concept, fairly simple idea to apply. Now, the reason in this class most of the time we don't care about distance is because it's super small. We don't ever have to find this actual number. We just have to compare two things to each other. And we'll do that here. All right. So here is a typical question. What we're saying are these are going to form ionic bonds. I want you, it says, of the following pairs, which would you expect to have the highest lattice energy when they form an ionic bond? Explain your reasoning. So one of these pairs will be higher, well, the highest. So we're answering two separate questions. Pick the one with the highest lattice energy here. Pick the one with the highest lattice energy in the second one, and see if you can do that and justify why you chose those two answers. If you need to, please talk it out with your lab partner. All right, so let's make sure we talk these out and that they make sense to you. So the first one is testing your knowledge about which part of the equation? The distance. All right? The reason that you know this is these are all plus 1, minus 1, right? So the top part of the equation is just going to equal a negative 1. By the way, let's throw this in there so you know this from now on. A negative force is an attractive force. A positive force is an ugly force. Just kidding. It's a repulsive. So when you get that sign, like Coulombs-law explains why likes repel and opposites attract. Okay, coming back here. So up here, our numerator's the same every time. So what we have to do now is know which one creates the smallest. These were all the same, so that doesn't matter. So of these three ions, which one of them is the smallest? Li. So LiCl would have the highest lattice energy. Did everyone have that correct? It's very logical and reasonable, meaning you can reason your way through that. You okay with that? All right, then this one, +1, -1, +2, -2, +3. Whoops, I don't know why I did that. That's still -1, and -1. So this one overall will be a -1. This will be a +2, and this will be, I'm screwing up a lot today, -2 and -3, right? All right. All right, now we can worry about the distance. It will be this answer by a mile, though, for two reasons. Mostly because much higher charge, much higher answer in your numerator, right? But aluminum actually is smaller than Na as well, right? So this one is for both. So who had AlCl? Okay. Don't overthink lattice energy. Just put lattice energy into your new constructed knowledge of Coulombs-law and have at it. We all right with that? Okay, on the previous test, I had questions like this, and then I had this question in the multiple choice. So read this real careful. All right, who has an answer? Can you really read that, Young, and do this at the same time? I'm not underestimating him. He underestimates himself, but I am not. All right. So the lattice energy increases as the atomic radius does what? Decreases, and as ionic charge increases. All right. Now, I'm absolutely sure that there are exceptions, but I know for once you don't need to worry about exceptions. Okay, this is what we just said. As long as you get this, we're fine. Lattice energy then increases with the charge on the ions. It also increases with decreasing size of ions. So here are our values. I asked you that one, and what else did I even have? Over here. Okay, but that was the different question. Oh, RB was the other one. It's not listed, right? But you can see LiCl was definitely larger than NaCl. What? No, there's lots of other bonds. It's just the typical one. If we're going to do a lab or some sort of activity, fluorine's too dangerous, bromine and iodine are too expensive, so you just go with chlorine. Right. You okay with this? There might be one more slide on it. By accounting for all these three energies, ionization energy, electron affinity, and lattice energy, we can get a good idea of the energetics involved in such a process. And then there's this complicated picture that looks great to me. Let's move on. This phenomenon also helps explain the octet rule. Metals, for instance, tend to stop losing electrons once they attain a noble gas configuration because energy would be expended that cannot be overcome by lattice energies. So that, written in plain English, is that we're saying we can remove one and get energy back out in the lattice energy. But for sodium, once we try to remove a core electron, the energy required to remove that one is much greater than the energy given out by the lattice structure, so it won't happen. It really won't ever happen. All right? So there's lots of things that can help us understand the octet rule, ionization energy, electron affinity, and now this idea of lattice energy. All right, I think that's the end of ionic bonds. That's interesting. This word has been deleted. All right, it's really important. Hold on. That you have a very solid idea of ionic bonds. It's really important that, one second, you know that covalent bonds are very different. Yeah, go ahead.
So with the last energy, what does changing it from a solid to a gas have anything to do with bonding it?
Well, in order to get the two things to even break apart, you have to heat them enough that they become a gas. Because to separate a solid apart is next to impossible for us. So we first have to heat it, we get our liquid, then we get our gas, and now they are a gaseous ion that can be forced to break apart with energy. It's like trying to get a molecule of water from a chunk of ice. That won't happen. You have to melt it and then boil it, and then they're free to move. Is that right? Go ahead. Well, sure, with the hammer, but not, I haven't gotten one single atom out of it. I'm sure they have. Anytime you nail me to absolutes, I'm always going to live in a gray area. That's how I roll. Oh, those are my jazz tickets. Which reminds me, I won't be here tomorrow. You won't miss me. Tomorrow I have the strangest / coolest assignment I've ever had as part of my job. My job is to be a chemistry teacher, right? Well, tomorrow they're paying me to go to Vivint Smart Home Arena and announce a girls' high school basketball game at 12. So I get the whole day off. Yeah, they play right after, but that's a home game for Roy or whoever we're playing. Is it Roy? I can't remember. So their announcer gets to do that. But then I'm just going to hang out with my kid and go to the jazz game after. So I get to get paid to do almost nothing and have fun doing it. Sound good? Yeah. All right.
Favorite part of your job?
Favorite part of my job is finding ways to make money by not doing my job. This is on video. That was a joke. Favorite part of my job is working hard. No, but for real, I'll even mute this so you don't think I'm lying. Cool. I would hate it if you were little robots. What's that? Thank you. All right. Just make sure you understand something here. Spend all this time building your framework about an understanding of ionic, and you got it, and now we're going to talk covalent, and you're going to try and force covalent into your understanding of ionic. That doesn't work. Okay, and in normal chemistry, maybe in this class I've already used this, but if your entire life all you did was play soccer and then they threw you in a baseball game, would you try and kick the baseball? You would have you couldn't assign the rules of one game to the other besides maybe you can't kick someone in the face. Maybe that's a universal rule in both. But they have different rules. Now, they're sort of similar. There's a ball. You want to score points. You want to hit it. Hopefully not let it hit you in the face. So there's some ideas, but make sure that you know An ionic bond has its rules, and covalent bonds have their rules. Now, they're both bonds. They both have electrons doing things, but they're very different because these lose and gain and these share.
So it still takes energy to break covalent bonds.
It sure will.
So would it take more for a nonpolar?
We're going to learn all about that here. All right. The answer is more for a polar one, but that's tricky to answer. So here we go. A covalent. First off, in covalent, we're going to learn that there are two types of covalent bonds. And I'm trying to time today so that we get to the exact moment that last year I started the video that I recorded last year. All right? So if you're like, why does he suddenly randomly stop right here? That's so they can hit play tomorrow and you'll be just bored out of your mind for 53 minutes listening to me talk to people last year. I know Levi Port, I talked to him in the video. That's the only person, because I previewed it. He did. He's a lot smarter than I think people think he is. All right. In these bonds, atoms share electrons. That's super different, right? But let's think about it. A metal has very few valence electrons, right? So it is to its advantage to just get rid of them instead of gaining, right? But a nonmetal has lots of valence electrons. If it's only one away, if it finds someone else that's one away, they can share. And now they're both full. All right? So the reason they will share their electrons is because they have a lot of valence electrons. You with me so far? All right. So that's the number one difference, is they are sharing instead of losing and gaining. There are several electrostatic interactions in covalent bonds. There's an attraction between electrons and nuclei. So literally, you'll have two nuclei. The electrons in both atoms are attracted to both nuclei at the same time. All right? There's also a repulsion between electrons, meaning that you just created a nightmare here. There was 7 electrons, and they had just barely gotten used to each other, and now you're going to hang out with 7 more, and now life just gets ugly. It's like the Brady Bunch gone bad. All right? And then there's a repulsion between the actual nuclei. Okay? So it's kind of a balanced disaster in a covalent bond, but it works out just good enough for both parties involved that they decide to keep together. You all right with that? Now, are they staying together because of an electrostatic attraction? No, that is an ionic bond. They are staying together because they are literally sharing a pair of electrons, or more than one pair, by the way, and that causes them to not ever really want to be apart. Unless they can find a metal. Yep, so they can have it all to themselves. Why share if you can steal? Right? That really is chemistry right there. So you have like chlorine gas. It's a covalently bonded molecule called a diatomic molecule. We drop in a chunk of metal, and both parties are like, why are we sharing? We don't have to anymore. Let's go take theirs. And then we'll be set.
So in a polycovalent bond, how do you know if there's only one metal? How do you know which one will steal from the metal?
You would have no idea. It wouldn't matter, but yeah, you couldn't be able to determine. All right, we okay with this so far? All right, so covalent bonds share electrons, bond between two nonmetals. Let's just do this again. So we had C. I don't even know. O and O. It doesn't really matter. But this is how these will work. First off, to know it's covalent, right off my little red flag, how would I know that this is a covalent bond? We don't know they're sharing yet because they're both nonmetals. Okay, which means now they'll have to share. Yeah, well, the squares for right now are probably just confusing. Let me get rid of them for a second. That worked well. Ooh, this is like three-dimensional. I could do this all day. Make me stop.
Keep doing it, Davidson. Squares. How much would it 34?
Ah!
Get more.
No. All right, here we go. So, how many electrons does carbon have? 4. And it might annoy you, but I'm going to put them right here. How many does oxygen have? 6. It might annoy you, but I'm going to put them right here.
Why like that?
Because that's how it is. But why like that? All right, it's our squares. If I share them in this way, where carbon shares its 4 electrons, 2 to one and 2 to the other, and then oxygen shares a pair, then right there, and then right there. Everyone involved now thinks they have how many electrons? 8. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This carbon, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. They were all able to obtain a full octet, even though individually they were nowhere close to a full octet, right? This would be the Lewis dot structure for carbon dioxide. Now, this is in a later chapter, Young, but if you wondered why I put them on the corners, it's because the places that electrons live, they repel each other. So there should be a 120-degree angle between each pair of electrons if you're only sharing them in 3 places. And you'll learn that. Like right now, that might seem weird. Actually, it probably makes perfect sense. But we will learn that a lot more tricky in chapter 9. Okay? Now, if you'll notice, I might as well do it right now. If you notice right here, carbon was only sharing in 2 places, right? So we would expect there to be a 180-degree angle between the 2 pairs. Not pairs. They're called bonding domains. We'll learn about them in chapter 9. What's that? The electron can travel, but typically in a covalent bond, it will stay between one set. The exception to that will be a resonance structure, which we'll learn about tomorrow.
So with the polyatomic ion, a lot of them covalent bond.
Yeah, they're all covalently bonded. And what they'll do, they share their electrons, but what they'll do, so let's pretend, well, I don't need to pretend. Let's put another pair back. CO3 would be right here, right? But C wouldn't have another pair to share, right? But O would have its 6. So in order to work, CO3 would need 2 electrons, right? So that's why we call CO3 carbonate with a -2 charge, so that there is a pair of electrons to complete the octet on the 3rd oxygen. And where do they get them from? Like magnesium. Magnesium carbonate. Magnesium would give its 2 electrons to the carbonate so that it could be in its C to 3O relationship. Yeah, it will find a polyatomic ion does not really exist until it is paired with its non-metal, or sorry, with its metal. I just blew that. Not really. Like there is a real thing, carbonite, and it's a mineral, but it's not CO2. It's just called carbonite. What's that? I don't know its structure. I'd have to look it up. Say that again.
With like 2 carbonates, I said they would
They wouldn't really share. What you would have in this process, you would have magnesium reacting with excess carbon dioxide. And it would require some form of energy. And that energy would, in this whole combination of things, it would break up a carbon dioxide and add an O. Well, it doesn't have to be, it could be carbon dioxide, excess oxygen. It doesn't matter. It just has to have the perfect conditions and you'll make it. Carbonates are very common though, so those conditions, they exist. They existed in the early formation of this planet. All right, this one might have been a little complicated, but what's that? Good. If I put a chlorine right here, we know that chlorine's a diatomic atom, right? I don't know why it does that sometimes. Then I'm going to put one right here. It's definitely to the advantage for both chlorines to hang out with each other, right? All right. But if I were to bubble this through water, the chlorines don't want to be together. They react with the water and now form HCl. Because chlorine would much rather share with hydrogen than another chlorine. If there was a metal present, so we dropped in sodium, it would much rather steal from Na than to share with another chlorine. It will do anything it can. Now the explanation here is that H is less electronegative than Cl. So if Cl shares with H, it doesn't have to share as equally. It can have the electron most of the time, and we'll talk about that tomorrow. Are we out of here in 2 minutes? All right. So we will pretty much tomorrow, we will be on this slide. It's going to try to explain to you the difference between a polar bond and a nonpolar bond. And simply stated, if you have two atoms with very little difference in their electronegativity, they will share pretty much equally, and we call that nonpolar. If they are far apart in their electronegativity, we call it polar. Because chlorine is much more electronegative than the H.
Do you want me to just read these here? Just check.
Sure.